physics goers, today we'll be discussing seesaw physics with rotational motion and elements of torque. Enjoy!
Okay, kick. 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 Don't do it that fast. I'm gonna fall off and I'm kidding. Hey!
To begin, a seesaw is a basic lever with a fulcrum or pivot point. According to the first law of Newtonian rotational motion, an object that is in constant motion will have a constant angular velocity, which will mean that there's no external forces. And according to the second condition of equilibrium, an object with a constant rotational motion, just like this, will have a sum of the forces equaling 0 and a sum net torque equaling 0 as well. First, we should define some terms. Angular acceleration is the change in angular velocity over time, and angular velocity is the change in angular displacement over time. Angular velocity is denoted with the omega symbol, which looks like a W, and angular acceleration is denoted with the alpha symbol, which looks like a fish. Whenever a child or anybody gets onto a seesaw, they exert a force downwards on the seesaw, causing it to rotate. The force of the child or the person can be found with mass times the force of gravity, which is 9.8 meters a second squared. And this alone is not what we call torque, but torque is the rotational length or the rotational arm times the force exerted. So we would take the measurement of how long this amount of the seesaw is from the pivot point or the fulcrum to where the force is exerted times the amount of the force to find what the torque is. Now let's talk about balancing a seesaw. Let's say we have a child of 30 kilograms, which is their mass, sitting about 2 meters away on the seesaw. If we calculate their force, which is mass times the force of gravity, which is 9.8 meters over a second squared, then we have 294 newtons of force pushing downwards in the clockwise direction. If we times that then by the radius arm length, which is 2 meters, we have 588 newton meters as the torque force. Now, this obviously is now an unbalanced seesaw, so we would need a child either of equal mass sitting an equal distance away, or a child of greater mass sitting a lesser distance away in order to create the same amount of torque in the opposing direction or the counterclockwise direction. With torques that are equal, we would have a net torque of 0, which would then create a balanced seesaw. With the children on the seesaw in the last example, we can see that torque is an inverse relationship. With a greater force due to the greater mass of the child, the lever arm distance can be shorter on this side than on this side in order to create equal torques. It is also important to note that the force applied should be perpendicular to the lever arm in order to create any torque at all. If a child came up to the seesaw and pushed outwards, creating a force that is parallel, there would not be a torque created. Lastly, due to the second law of Newton, there is the equation that the net torque is equal to the moment of inertia or rotational inertia times angular acceleration. By the end of this video, you understand the basics that go into the motion of a seesaw, including elements of torque and rotational motion. If not, feel free to ask me or Miss Kendrick, and see you again, physics goers!
Let's just go with the flow, Go with the flow. Oh!